Hello, Chemistry Tribe. Today we are getting into light and quantum mechanics. And so to start, we have to understand, what light really is, right? And it is basically electromagnetic radiation. Basically a type of energy. And that's where we get into this notion of photons. And this energy, type of energy that, has oscillating basically electric and magnetic fields. As from the sound of that, you can think, oh my gosh, this is really confusing, right? And this is something that Einstein played around with, the idea of photons and light and these packets of energy. So if Einstein's grappling with this, I'm sure, it's a tough topic, right? So, but that's the idea that we have light. It's electromagnetic radiation. It's a type of energy. And on the, low side, well, okay, it has these oscillating fields. Let's just define the idea of photons. And that's what Einstein called basically packets of energy. Really, this is, light, but, packets of energy is fine because, these packets of energy have the idea of wavelength and frequency. So there's a correlation between this idea of energy and then wavelength and frequency, which we'll get to in a little bit. So we got light, we have photons. Photons, this idea of packets of energy, right, which is thank Einstein for. And now, one thing that we should understand in going forward is, right, that there is a speed of light. So we can actually relate, a distance to time, ratio. The speed of light is often given the symbol little c and a value of 3.00 times 10 to the 8th meters per second. There are more accurate values than I'm displaying currently here with the speed of light, 2.998 times 10 to the 8th meters per second. So just, for lecture's sake, keeping it simple. So we have this idea of photons and light, packets of energy, speed of light, and so if we were to look at like a photon, and this, idea of them possessing wavelength and frequency, we could maybe draw a crude axis here. And we would have basically this type of oscillation. Right, and it could keep going. And so we should see, sorry for my rough cartoon, but some symmetry here, and basically the idea of like a cycle, right? And so if we look at the notion of maybe starting from here in pink, going all the way over to the next pink, right? That would be one cycle or one repetition, right? And so we see that as we go right here throughout, right? So we see this repetition. That's really a cycle. If we look at, I just do the crest to the crest. I mean, you can do, as long as you're going to one symmetry element to another, this distance is your wavelength. So we have a couple different pieces, to characterizing the wave, if you will. So we have a cycle, right, which basically represents the the reproducibility. In the wave function. We have this notion of wavelength. And wavelength is given the symbol lambda. And wavelength is basically that distance, as I was saying. Right, it's the distance between crests, adjacent crests. So that's our wavelength. We also have frequency. And frequency has this mu, or this kind of funky V symbol. And basically this is looking at, the number of cycles that you basically pass by like a stationary point. Every second. So if we'll get into units in a little bit here, but if we're looking at units for frequency, that's this notion of cycles per second. And with wavelength, this is distance. This is a form of, meters. If we go back up to the wave function and get a notion of now, frequency, we could say that, like here is a stationary point. And we have to think of this wave function now as being active and moving. And so it's how many of these cycles or these purple dots actually go by that stationary point or that blue star every single second. So we have our cycle, which is the reproducibility, the symmetry of the wave. We have, distance from crest to crest. That's our wavelength. That's in some form of meters. And then we have frequency, which is basically almost how fast it's going, if you will. How many cycles pass by a stationary point every second. There is also the idea of amplitude. Which we see here. It's also, if you will, a distance. We won't be playing too much with amplitude. but amplitude is basically, peak height. The taller the peak, the brighter the light. So there's our base notion of wavelength, frequency, and amplitude. Be honest, we won't be dealing too much with the amplitude idea. As an addition here to frequency, cycles per second is often given the unit Hertz or Hz. So that takes us now to our electromagnetic spectrum. Of which we see very little of. So we're going to relate this in terms of wavelength, in terms of meters, basically decreasing as we're going here from left to right. So we can start at the very far left, and we're looking at now wavelength, large distances between the actual peaks, maybe to roughly about 10 to the minus 1. And so here we have radio waves. So picking up stations on your radio, etc., right? This is the wavelength that those particular photons are have as far as their physical property. We get now into the smaller, from 10 to the minus 1 to 10 to the minus 3, we have microwaves. And I'm sure we've all used a microwave in our day, right? It's not new technology anymore. And what we're doing there is really exciting the oxygen-hydrogen bond that's present in the water molecules within the food. And that excitation is causing now energy to be transferred to the food, or the food basically cooks. Basically cooking from within, if you will. So that's the idea of microwaves. We then get between 10 to the negative third and 10 to the negative 6, and now we're looking at infrared. As far as a lot of technologies, from cell phones to remote controls, have a lot of infrared technology and sending signals, or sending energy essentially to flip a switch. So we have that infrared region. And then continuing forth, we're right around 10 to the negative 6, and this really small window here between 10 to the minus 6 and 10 to the minus 7th is actually where we have our visible region. Right, and that expands into the different colors that we have. If we're in still wavelength, but now looking in terms of units of nanometers, we can kind of look at the spectrum. Range goes from 750 to about 400 for us, and they just going down by 50 unit increments. Because I should have had more of a break there to my visible spectrum. And so we're basically looking at the different colors that we're actually going to be getting, right? As far as Roy G. Biv is concerned, right? We're in this red area, then orange, then yellow. So there's our Roy. And then we get into green, blue, indigo, and violet. And so that's just what we see. So that's the layers within our very small level so far of the electromagnetic spectrum, right? There's radio waves, microwaves, infrared, right? We can't tell any of that. And now expanding to 10 to the negative ninth. This is now where we're in the ultraviolet region. These UV lights, black lights, things of that nature, right? Looking at those types of wavelengths. We now are getting into some more heavy types of photons. If we get to 10 to the negative 11th, now we're talking about X-rays. X-rays, right, can pass directly through you. So we're getting more powerful as we go. And then lastly, we would be around 10 to the negative 15th. And this is where we now have gamma radiation, gamma rays. So if we think about, wavelength, right, there's now some inherent energies that we have to start to consider, right? Because radio waves, we're being exposed to radio waves all the time. Radio waves are all around us, but yet there's no issue of that, in terms of health or anything of that nature. But yet X-rays, gamma rays, and even ultraviolet light, right? All of those cause breakdown of tissue, of organic tissue. In terms of ultraviolet light being in the sun too long, you get burned. Gamma radiation actually, destroys tissue. X-rays, not that it destroys tissue, but it passes directly through the body. Right, the X-ray person that's helping you there is always in another room, and you always have a big lead, protective layer on your heart and wherever, because you're getting hit with some heavy heavy energetic particles in terms of X-rays, and then even going further to gamma rays. So this is almost like an energy spectrum as well, like that we have very, very, we have waves of not much energy, radio waves, and then we have waves that are extremely high energy, which would be then gamma rays. So we have the relationship between, wavelength and energy. But also frequency. And energy. So in terms of waves, right, for waves, your frequency and wavelength are tied to one another. If you know one, you automatically know the other. And the reason is just the relationship between that and the speed of light. So here we have frequency is equal to c over lambda, or we have lambda is equal to c over mu. So here we have our frequency as well in the equation on the right, and then below is where we find that idea of wavelength. Or solving for it in the equation on the right. And then between the two, we have the speed of light. So that allows us to go between one and the other. And so that also means then that there is a relationship between frequency wavelength and energy. And so here would be our expressions for the energy of, a particle. And so here are the two different forms that we could use. Both are relating to energy of the particle, and since wavelength and frequency are inherently related to one another, right, it's just using the equations that we have above as far as that is concerned in terms of relating the two. So, here is our energy of the particle with relation to frequency. And then here is our equation with regards to wavelength. We have c, which we've already talked about, which is the speed of light. We do have this new species called, h. H is looking at basically Planck's constant. Which is equal to 6.626 times 10 to the negative 34th joule seconds. And so that's what we see above as well. So there's a lot of equations here, really, 4 of them, but they're all really tied to one another because of the first two, is that we have that inherent relationship between frequency and wavelength, and since we can also relate energy to that, well, that's why we have two expressions to describe that as well. One thing to remember is the energy per particle, or in that particle sense, is in a per particle unit. Usually energy would be in joules per mole or kilojoules per mole. So often, there is a conversion using what we learned earlier, right? Using Avogadro's number. right? That idea of 6.022 times 10 to the 23rd things per mole. So let's look at an example of maybe bringing that all together. So let's say that, you know, the light, really the orangish glow from sodium vapor lamps these are usually these, you know, big, you know, parking lot lights. They have kind of an orangish glow. If they do, these are sodium vapor lamps. And so the orangish glow from the sodium vapor lamps occurs at 582 nanometers. What is the frequency of light? And also, what is its energy per mole of photons? So we have two kind of questions here. Start with the first one. We could look at, okay, well, you know, the frequency of this light. So we're really looking for, you know, this idea of frequency. And we could say that that's, you know, part A. And then we also have this notion of what is its energy per mole. And so that would be going to B, where we would want to have that energy in a per mole basis. So that would be part B. What are we given? Well, we're given wavelength. We know what our wavelength is actually equal to. So if I look at part A, and I'm asking myself, well, what is frequency? But I know wavelength. Well, that's pointing to me to this conversion that I can plug that value in of the 582 in for my wavelength. Now, one thing we want to be careful of here, we need to be careful of units. For instance, C is equal to 3.0 times 10 to the 8th meters per second, but our wavelength is equal to 582 nanometers. So we have a problem there with our units. So the first step would have to be here is to convert wavelength from nanometers to meters. And then step 2 would be to use our equation to then solve for the actual frequency. So let's start with that idea of step 1. So if we have 582 nanometers, right, we need to convert that. We know that there's a relationship between the two, right, that for every 1 times 10 to the negative 9th meters. That's 1 nanometer. And so my unit of nanometers is canceling out. And now I'm in terms of meters, or 582 times 10 to the negative 9th meters. So that's my first step. And now my second step is to plug that into my equation. We have our speed of light. We're now dividing it by our meter value. And then we're basically left in terms of frequency, or reciprocal seconds, or cycles per second. And we get 5.15 times 10 to the 14th Hertz. Again, just as a reminder, Hertz is equal to cycles per second, or 1 over seconds. And so that's where that Hertz term comes into play. So that's part A, right, is looking at, okay, what is our value of our frequency with this orangish glow. And so there's part A. Part B right now was asking that question of energy. And we were looking at energy in terms of maybe 2 different units. And so we really have 2 choices here. We could start with our energy of the particle is equal to Planck's constant times frequency. We just got that frequency in part A. Or, to be honest, you could use hc over lambda, where lambda is already given in the question. So it doesn't matter which one. I'm just going to pick the one on the left. So I'm just picking one. Like I said, it really doesn't matter. So that energy of the particle is going to equal Planck's constant times frequency, or 6.626 times 10 to the negative 34th joules seconds times 5.15 times 10 to the 14th Hertz. Or remember, that would be reciprocal seconds. So notice that's how the seconds are canceling out. And really we're left with this joule unit. Meaning that we're just really looking at one particle with this particular frequency, this particular wavelength. And we end up with a value of 3.41 times 10 to the negative 19th joules per photon, right? Remember, the photon is giving us, the orangish glow, right? So now we have an energy associated with that, and now it's just a conversion. We are in terms of per photon, so we just need to use Avogadro's number to now get it in terms of per mole. And this gives us a value of 2.06 times 10 to the 5th joules per mole of photons, or 206 kilojoules per mole of photons. So that is your answer for part B. Really just showing you the inherent relationship between frequency and wavelength, right? It's automatically that you know one, you know the other. They're interconvertibly, accessible, and then plugging it into the energy equation, we have a choice. So it's up to you which one you actually prefer. Here I just chose the frequency version, but nothing wrong with doing the other way. You will get the exact same answer. So that brings us to the photoelectric effect. This was something hinted to in our brief history. Millikan discovered the photoelectric effect, and it's basically the ability to dislodge electrons from a metal as a result of shining light on that metal. That is the photoelectric effect. Every metal has a threshold frequency. So and what is that notion of threshold frequency? Well, basically threshold frequency is an energy, if you will. Basically, it's a frequency if below electrons are not ejected. If above, then electrons are ejected. So it's just saying that there's a threshold for this, for it to actually occur, and hopefully that makes sense, because we have different elements, we have different metals, and they wouldn't have exactly the same in terms of this photoelectric effect and this threshold frequency. The electrons about a metal are held to different extents. Some are held a lot tighter, more energy holding them, if you will, to the nucleus compared to other, say, metals. Threshold frequency is related to, binding energy. Right, and so this is the energy required to remove an electron from a metal. And we know that they're basically related to one another, right? The idea of energy and frequency. So our binding energy is given this capital phi. And that is equal to Planck's constant times my threshold frequency. And so basically the binding energy, if you will, you could think of as a threshold energy holding electron to the metal. Right? We must surpass this for the photoelectric effect to occur. So let's look at this maybe in more of a diagram sense. So here we have the photoelectric effect. See if I can make it a little bit bigger here for us. Still see the equation at the top. And so if we look at the part A of the photoelectric effect as far as below on the left, right, we can see that we have this notion of light, right? We have photons coming in. They have a wavelength, they have a frequency, and then that causes now electrons to be emitted. Right, so that's just the base idea of it. We shine light. Remember, photons have energy, right? They're packets of energy, and they can supply enough energy to cause electrons to be dislodged or ejected. But it depends on the metal and the energy holding the electrons to the metal. And so that's where this notion of threshold frequency comes into play. So if we actually look at the experiment on the right, I'm just going to expand this so you can really see more of the intricacy of it, is that on the right we have basically at the very top a tube that is an evacuated chamber. And we have a metal on one side and a terminal on the other. If you kind of follow the diagram around, you have basically a positive terminal that's hooked up. We have a negative terminal as well. Right, and so we have all the makings here of a circuit. But the difference between the two is that, that we have space in between the one positive terminal and the other negative terminal. In this case, the negative terminal would be now our metal surface. So we shine light on this, and nothing happens, right? Nothing happens. And eventually, if we keep increasing the frequency, eventually, all of a sudden, we see electrons actually going across from that metal plate over, and then all of a sudden, we have current being displayed, right? And that's what we're seeing, that there actually is a circuit. So that's the photoelectric effect. We shine light on a metal. It has to have the appropriate frequency, but once we are there or past that frequency, we now cause electrons to be ejected. And we can see this through this demonstration of the photoelectric effect as far as showing how we can actually complete a circuit even though there's space in between two of the electrodes, as we see on the right. So that is the photoelectric effect. It also means that if you are shining, light of a frequency that's greater, that's basically is greater than the threshold, now these electrons have kinetic energy. And that kinetic energy is due to the difference the difference between energy of light and your binding energy. So we could say that the kinetic energy of an electron is equal to Planck's constant times the frequency of the photon, the light that we're actually irradiating the sample with, minus our binding energy. Or one step further, where really we're just looking at a difference in the energies as a result of the threshold frequency and then the frequency of the photon that we're actually supplying. So let's look at an example of this idea of threshold frequency and binding energy. So our example is as such, right? We have the threshold frequency for a metal is 1.23 times 10 to the 15th reciprocal seconds. Remember, that's also Hertz. What is the binding energy? Per mole of electrons. So here, if we look at our question, let's see what we're given. We're given the threshold frequency for our particular metal. So we know what that is. And what we want to figure out is the binding energy per mole. So that means that we want to figure out the binding energy, but that's usually joules per particle. So that means we would have to do another step to get to joules per mole of particles. So we really have, two steps in order to kind of go through this process. The first step would be just to plug into our equation of binding energy, which is Planck's constant times our threshold frequency. And then the second step would be to do the conversion that we need to do. So for step one, our binding energy is equal to Planck's constant times the threshold frequency. So here is our Planck's constant, 6.626 times 10 to the negative 34th joule seconds. We then have our frequency of 1.23 times 10 to the 15th reciprocal seconds, and we end up with a binding energy equal to 8.149 times 10 to the negative 19th joules per electron. And so here's where we now get into step two, which is the conversion. By taking that value that we just calculated in the first part, now breaking out the units so we can use dimensional analysis to convert from the per electron to now this idea of moles of electron. And so if we do that calculation, we end up with 4.90 times 10 to the 5th joules per mole. Excuse me. Or 490 kilojoules per mole of electron. And so that is our answer as far as the conversion between now binding energy and frequency, threshold frequency.